Let's look at how energy is transferred. When we look at the energy skate park, we saw the object, the skater, go from a high position to a low position, and the whole time speeding up. When an object speeds up, we know that the changing speed means that there must be an acceleration. An acceleration then means there must be a net force acting on the object. When our skater is at the highest point and not moving, remember from the experiment that the skater is at rest at the highest point. So at the highest point, that's when we will see that the force on our skater is the gravitational force. And that gravitational force is going to be acting on the object, on the person, the whole time the person or the skater is in motion. So I'll draw that over here. And so as this person moves through this height difference, this change in position, this gravitational force is the net force on our skater, and that net force means that there's an acceleration, and again, that acceleration means that there's a change in the velocity. And we saw that at the bottom, our skater was going the fastest, and the energy stored in the system at that point was all energy of motion or kinetic energy. And when our person was at the highest point, it was all energy due to the gravitational field. So there is a connection between this change in energy and this force. When a force is applied through a distance, then the acceleration will cause the object to have a change in speed. So let's look at a graph of force and distance. If the force applied to an object is constant for a distance d here, that force, remember, is causing an acceleration. So this force would be equal to m times a. When the acceleration is multiplied by distance, we get a change in the velocity. So if you remember from our study of motion before, the v squared is equal to v, so v final squared is equal to v initial squared plus 2a delta x. And so this a times delta x is the same as a times d, and notice that we have a difference in velocities. So when a force is applied to an object over a distance, so here's my object and here's my force, and that force is acting on the object for a distance d. That force is going to cause an acceleration, and an acceleration means there's going to be a change in the velocity. So the force will cause an acceleration, and the acceleration means there will be a change in velocity, and a change in velocity means that there will be a change in the kinetic energy. So when we take the force and we multiply it by the distance, that force is doing work. So we define work in physics as being the product of the force and the distance. So force times distance. Now from our graph, if we take the force and we multiply it by the distance, that is equivalent to finding the area under this rectangle. So let's dig into this force and work relationship. So if this is a net force that causes this change in velocity, then equal to m times a, and then we're going to multiply by d, so this is substituting in for the net force, and that would equal our work. I'm going to just abbreviate work with a W. Now, D could be written as a change in position, a delta x. So then I would have MA times delta x is equal to our work. Now, earlier, I reminded you that we had V final squared is equal to V initial squared plus 2A delta x. So, I see an A times a delta x here and an A times a delta x here. So, let's solve for this A times delta x that's over here in terms of the velocities and constants. So, this would be V final squared minus V initial squared. Subtract the initial square from both sides, and that will equal 2 times A delta x. Now remember, I'm going to leave A delta x together because that's what I want to substitute into over here. So I'm going to divide by 2 on both sides. So I'll have V final squared minus V initial squared divided by 2 is equal to A times delta x. So now let's substitute that A delta x expression over here. So we're going to take what we have here and we're going to substitute it in for this A delta x there. When I do that, I'll have M times, I'm going to use a parentheses here, so V final squared minus V initial squared over 2, and that'll be equal to the work. Now let's multiply our mass in, so we'll have MV final squared minus MV initial squared all over 2 is equal to the work. And then I could rewrite this as being MV final squared over 2 minus MV initial squared over 2, and that would be equal to the work. And notice this begins to look familiar. So MV squared over 2 is the same as 1/2 MV final squared. And then I would have 1/2 MV initial squared, and that would be equal to the work. Now, earlier we defined this 1/2 MV squared as being the kinetic energy, or the energy stored in the motion, and because it's a final velocity, it'll be our final kinetic energy, and then minus, this will be our initial kinetic energy, so EK initial, and that will equal the work done by this net force. Now we can write this as the work then is equal to the change in, remember delta means the change in kinetic energy. And we call this the work energy theorem.